Hello! Today we're going to be talking about the twins paradox, first theorized by Albert Einstein in 1905 and then further elaborated on by Paul Langevin and Max von Loo. The twins paradox tests our understanding about special relativity and the very nature of space-time. Suppose we have two twins, Alice and Bob. We put Alice in a spaceship and send her far away at a constant speed close to the speed of light. She then turns around and flies back to us. Let's break this down into two parts, flying out and coming back. Well, we know using Einstein's equations for special relativity that proper time, which Alice measures, is multiplied by the Lorentz factor to give improper time. As a reminder, proper time is a time clock where both events happen in the same place. This means Alice measures the proper time. So if we send Alice out at 75% the speed of light, or 0.75 c, her Lorentz factor, or gamma, becomes 2. This means if she measures herself taking 5 years to reach the end and turn around, we will measure 5 times 2, or 10 years. We can apply this again for the trip coming back. She will measure herself to be 10 years old, but Bob, who has measured the time on Earth, will measure her to be 20 years older. Pretty neat, right? But here's the problem. From Alice's point of view, we're moving away at 0.75 the speed of light in the opposite direction. So according to Alice, the two events, us leaving and us reaching, happen in the same place for us. So we should measure the proper time. This means that we should expect her to be older than us. If the journey takes us 10 years, then according to us, Alice should be 20 years older by the time she comes back. But she isn't. How can this be? The answer lies in Alice's switch of inertial frames halfway through the journey. She experiences acceleration, which is a non-inertial quantity. The laws of special relativity don't say anything about moving clocks in a non-inertial frame. This is where the time gets accounted for. I just want to make it clear here. Alice is not younger because she accelerates. She's younger because of the breakdown of our assumptions for time dilation that happens during the acceleration. Just for fun, we can add an acceleration and show how this affects time dilation. It should increase it. I'm not going into the math for this. It's beyond the scope of this video, and quite frankly, it'll take too much time. But the equations that truly depict the time taken by Alice are given as follows. For those of you who are interested, we get these by integrating rapidity and plugging this into the time dilation in differential form. This with the boundary terms, of course, but I've left them out here for simplicity, as that can get very messy. These equations describe one direction of motion. We can multiply it by 2 to get the time in both directions. For illustration's sake, let's say we accelerate at 60 hours to 0.8 c, or 80% the speed of light. Both equations agree that it takes about 10 days for Alice to reach, according to Alice. But the standard time dilation says Bob sees Alice take 16 days, whereas the time dilation formula, which includes acceleration, states that Bob sees Alice taking 26 days. The acceleration adds 10 full days to time dilation. Notice how our acceleration line is below that of standard time dilation. Most of the journey, Alice will think Bob is aging slower than he actually is. Until she slows down, that is. While she is slowing down, she will then see Bob in fast forward. This extra time is the time that Bob needs to account for. That's acceleration for you. This adds the time dilation and ends up being the term that accounts for the twins paradox. There you have it.